It's a great pleasure to have Professor Peter Constantin from Princeton, who's going to tell us about remarks on Navier-Stokes equation and Euler equation in context of turbulence. And Peter, we have 50 minutes, then 10 minutes for discussion.
Yeah, so you can stop me like 2 minutes before 15.
2 minutes or 5 minutes?
5, that's fine. 5.
Okay, very good.
All right, thank you. So first of all, thank you very much for the invitation. I am thrilled to be able to talk to you. I'm not so thrilled that I'm not in Cambridge. I remember fondly quarter a century ago when we had a wonderful meeting with Charlie Doering and Idris and a whole bunch of people at the Institute. It is a challenge for me to give this talk in view of the fact that the audience is so mixed and so interesting. So in some sense, I have a math talk. I will try to explain things, or rather talk to the experimentalists and the practitioners while the slides are addressed more to people in math. But I will try. I'm hoping that although there's a mixed audience, I'm really thrilled to be able to talk to both audiences. So one of the reasons is that I think that analysis, PDE analysis, and experimental turbulence are closer than theory. So I feel, at least personally, closer to the experimentalists than to the theoreticians, because we both in analysis and in experiment, we end up by giving, let's say, something that sounds like a definitive answer, but the doubts and uncertainty come when you go and look under the hood. And I'm very impressed by the fact that the experimental community has a commonality of results, which is really the remarkable thing. There is a commonality of results despite great deal of variety of challenges, experimental technical challenges and conditions. So I think that it is a very good strategy to emphasize those. In mathematics, we don't have essentially what are the sources of doubt are not if there is no mistake, of course, if there is no mathematical error. The sources of doubt have to do with the nature of idealization. So to my mathematician friends, I always found inspiration in experimental data, but the way I always approach them, and I try to approach them, is with the same, looking at them with the same seriousness as you look at the mathematical assumptions. So, and not as an excuse for some esoteric math. So essentially, if you interpret, the challenge is to interpret correctly what is found. So I think it is relevant. I'm not entirely sure, but I think it's relevant to look at turbulence from the perspective of the fundamental models. The fundamental models are the Navier-Stokes equations, which are written here, incompressible Navier-Stokes equations in 2 or 3 dimensions, and the Euler equations. And you see here, by the way, do you see my little hand pointing here? Because it would be useful.
Yes, Peter, we see it.
So we took the density equals 1. So this already refers to the Princeton pipe experiment. Immediately you realize that the constancy of the density, when we just have such a huge pressure, is a major issue. So variable densities introduce some gradients of the density that might be really relevant, at least to my mind. So we're talking about the incompressible Navier-Stokes equations in which all this talk, the density will be 1, and the Euler equations, which are obtained in taking, strictly speaking, just the coefficient nu to 0. And we were going to discuss only classical no-slip boundary conditions in the case of Navier-Stokes, if there are boundary conditions. And when we were going to refer to absence of boundaries, that means essentially either the whole space with decay at infinity to some extent, or periodic in space. And for the Euler equations, the boundary conditions are always, if there is a boundary, non-penetrative. So the normal component of the velocity vanishes at the boundary. So there is a Reynolds number, which is made out of a typical velocity, a typical length scale, and the kinematic viscosity. And we're going to discuss a little bit about that further down. So there are many questions in turbulence, and the goals of what it matters in turbulence depends on the practitioners. Some people might want to suppress turbulence if they build cars or airplanes. Some people might want to enhance turbulence if they want to mix things. So in this talk, I will discuss only two basic problems in turbulence. So one is the anomalous dissipation, I think named by Greg, I don't know, by analogy to field theoretic usage, or the zeroth law, the same thing, named by Srini, that I know, by analogy to the very other famous numbered laws. And this I'm quoting from Uriel's book. If in an experiment on turbulent flow, all the control parameters are kept the same except the viscosity, which is lowered as much as possible, the energy dissipation per unit mass, time derivative of the energy, behaves with a minus, behaves in a way consistent with a finite positive limit. So that means that the expected value in some way of dE dt is minus epsilon, and it is not zero. The statement holds in the limit to infinite Reynolds number, and one needs to understand something. What do we mean by these funny braces? And from the Navier-Stokes equations, if you believe that the braces are space-time averages, then you get that the rate of energy dissipation is epsilon. So it's this nu times gradient u square is epsilon. So this suggests perhaps that as nu goes to zero, gradient u square has to go to infinity in the limit of Reynolds number going to infinity, so that we're going to come back to that at the end of the talk. So the second topic that I might touch on, and this is the only other turbulent topic, is related to structure functions. So again, quoting from Uriel, in a turbulent flow at very high Reynolds number, the mean square velocity increment between 2 points separated by a distance L behaves approximately as the 2/3 power of the distance in the inertial range. In the inertial range, I added, so it's not in the quotation mark. And as always, Uriel very, very cautious, both in the previous and this one, behaves like, okay, all right. So I am going to use here only modulus, so that I take the velocity at 1 point displaced by L, and then take the absolute value. I'm not going to get into the details of the structure function. So this is just for explaining the law from the point of view of what would matter to a mathematician. And that this expected value scales with no other parameter than epsilon, like the 2/3 power of the distance. And the inertial range is a range of lengths that at least exceeds a cutoff length. So this was discussed in the first talk in some place. The vanishing of this is at L goes to zero only if LD is left go to zero. So that is an asymptotic statement. And related to this is the famous Kolmogorov spectrum, in which again epsilon is the only parameter, and there is a prefactor, universal allegedly, and the power here is minus 5/3. And again, there is range of values of K, and the range of values is limited above by a dissipation, and the two length scales and the dissipation are, roughly speaking, related as inverse powers. So there is a dimensional analysis argument what they give you. So the 4/5 law, and that's why I was referring to the numbers law, is the exact quote unquote statement that the third moment is linear in the longitudinal moment is linear in L, which I wrote again with absolute values here, and the only parameter is epsilon. So the questions that I'm gonna mention in turbulence, and that's are the following, only two questions really. Is there a correct framework validating and predicting experimental evidence? So to the extent to which, you know, if there is universality, there should be a correct framework that predicts it. So is there high Reynolds number universality in an inertial range? So these are, I think, driving, at least from the theoretical physics point of view, if not applications, these are driving the study of turbulence as you know, Feynman would refer to. Okay, so related to the structure functions and related to the famous Landau comment about the Kolmogorov theory are questions of intermittency. So intermittency can be defined and is defined in various ways, which are not entirely equivalent. So one way of thinking about it is are corrections to the scaling of these structure functions. If they would stay Kolmogorov, then there will be no correction of the type length to minus alpha p. In this equality here, there's just algebra. So there, another way to understand this is if L is an outer scale and is given to you, in order to make the identification between these two quantities and epsilon is given to you, then U is defined by this relationship, okay? So one circles around these things in various ways. You can try to prove that there is a mean square velocity related to the mean dissipation, and there are some situations in which this is correct. So alpha sub p are intermittency corrections, and these are supposed to reflect intermittency. As I mentioned, there are other notions of intermittency coming back to the original objection of Landau, which had to do with sparsity in physical space of the quantity whose average is the dissipation. So I'm going to come back to that a little later at a different slide. So very little is known totally rigorously, and I even hesitate to put this result here. If you take Navier-Stokes equations, make assumptions, and the assumptions are of regularity and some bounds, and then you take time, you take space averages in various locations, uniform but local, the balls of radius rho, place those balls anywhere, take time averages, and then take initial data, arbitrary initial data, and then you can prove the inequalities that everybody believes that come from convexity. So in some sense, this is little more, or maybe no more than just reading the equations. So in contrast to the extent to which we want to link turbulence to Navier-Stokes and Euler equations, there are basic questions in PD, and I will ask only a couple, I think maybe three. So do singularities form in finite time in Navier-Stokes solutions from smooth and localized initial data? This is a famous problem. Some people might know that. It was famous before it became famous. And finite time is not an artifact. There cannot be an infinite time singularity without a finite time singularity. That's a theorem. So if you have some solutions that you can prove that there are solutions whose entropy grows nicely, mildly to infinity as time goes to infinity, then some other initial data will have finite time blow up. The second question is about the Euler equation. So you do this ideal incompressible fluid equation that is so idealized, and ask yourself whether or not those blow up. And then the third question would be, again, a question of universality. Can one have the Euler equations, which formally are the limit, as the infinite Reynolds number limit of solutions of Navier-Stokes equations when they're, let's say, boundary conditions? So are the Euler equations the limit, or are there non-universal defects? And by non-universal defects, I mean that depending on, let's say, boundary conditions or data, let's say, or shape of the domain, you might get different answers in the limit of zero viscosity, and the different answers have singular forces that change singular in space. So this is a slide reminding people, and again, now I want to, mathematicians know these things very well. I will want to talk to the experimentalists who know them as well, I'm pretty sure. So, but I want to make some comments about what they mean. So let's take the classical Prodi-Serine conditions, which are conditions on the velocity. So you take the velocity and you take some norm of the velocity. So you take a time t, measure the maximum of the velocity, square it, and integrate in time. And if that is finite, then the solution from a fixed initial data that is hidden in this discussion doesn't blow up. What does that mean? It means that given the time and the initial data, there is a guarantee of no infinity in the velocity, and therefore, by some mathematical tricks, no infinity in anything else that started out okay. So you're guaranteed to control, but that doesn't mean that you're controlling it by a quantity that is independent of the, let's say, a Reynolds number that you agreed on at the beginning. So it is not independent. It depends on Reynolds number that's bound. These are two extreme cases. One is when there is a time integral of the maximum, and here is the supremum in time of the L3 norm. And this was a result that was done much later than the Prodi-Serine result. It's a result of Escauriaza, Seregin, and Schwerak. Again, the same kind of assumption implies no singularity. In terms of the pressure, the hydrodynamic pressure, which is in this particular case the Lagrange multiplier for divergence free, the condition is in terms of the time integral of the L3 norm squared. So there are other conditions as well. This is very easy to prove. It was done by Berselli and Galdi, but it's a different condition in some sense, although of course each one implies the others. There are no such conditions for Euler equations. I'm going to discuss later. However, there is, so the difference between sufficient conditions, so this is what I was talking at the beginning, there is, you look under the hood. So this is, at this point, a conditional statement. The conditional statement is correct, but the assumptions are extremely strong. So in terms of the Euler equations, the assumptions have to do with momenta or the pressure, not with gradients of the velocity. And in the Euler equations, there are similar conditions, and one famous one is by Biel, Kato, and Maida. I'm going to repeat it in a second. And there is a nice unifying condition due to Alexei Cheskidov and Roman Shvitkoy. And I want to explain it in words here. So you are looking, assuming that things are okay, you are looking at the Littlewood-Paley component. So you are looking essentially at a window of wave numbers about 2 to the k times some length scale. So you cut off the velocity, and u sub k is really the velocity at around 2 to the k, or lambda k, to the q, sorry. Q is an integer. So now you are looking at the last integer, capital Q, depends on time, the last integer after which the velocity is small in some sense, and this is the sense in which it's small. So there will be such, if there is a smooth velocity in some way, there will be such a last Q. And then you look at the vorticity and you cut off everything that's above Q, and you measure that vorticity up to that Q, depending on time. You measure it in some space that resembles L infinity. It's not at all L infinity, but it's a space, a Bessov space that essentially tells you that you are measuring the magnitude of that thing. And if that integral is finite, there is no blow up. And the reason why this is nice is that on one hand, this is weaker than Prodi-Serrin, so it implies it. On the other hand, if you are in the Euler equations, this Q is infinity. There is no place, viscosity is 0, so there is no place where we're strictly less than 0. Q is strictly infinity, and then you return to the actually to return to a condition that strengthens the Bill-Kato-Maeda condition that is was proved also. So it's a slight improvement. So now let's return to intermittency. Intermittency was originally defined in terms of structure functions. In real life, there are two more definitions. One in which you are looking at the regions in which one important quantity is large, let's say the vorticity. You paint only the region where the vorticity above 90% of its average. And you discover that that region is kind of complicated and narrow in some ways. And you call that intermittency. You can take the gradient of velocity in terms, instead of the vorticity, take its magnitude. Now it's a matrix norm. You look at regions where that exceeds 90% of its average, and you discover that it is somehow sparse region. So these results here are theorems, and these are unconditional theorems. And they tell you somehow that this intermittency is limited. So the first one is a classical result of Voyage, Guillopin, and Temam from 80s that says that if I take m derivatives, and m can be any number, 1,000 derivatives of the velocity, and raise them, take them and measure them in L2, so square them, integrate in space. This is with periodic boundary conditions. And then take a small power of them. Like for instance, if m is, let's say 2, then you get here 2/3. Then integrate in time and assume, then this quantity is finite and is controlled by the initial energy and the viscosity. So the parameters capital T is arbitrary, viscosity is arbitrary, could be very small but finite, I mean non-zero, and initial velocity u at time 0 is a nice function, let's say a square integral. Then this object is finite, and not only it's finite, you can control, you can compute how large. And the consequences of this are that the ballistic, so how far can you move an object is limited. This is the velocity, maximum velocity in integrated in time. It's as far as, if you start from point A, how far you can go to point B is bounded a priori and without doubt. This is now, again, math without assumptions, or even the gradients to the power 1/2 are time integrable. So these are very limiting the intermittency. And by a different method, you can take, for instance, the Laplacian of velocity. And so this is not in L2, this is in L4/3, but on the other hand, the power in time is also larger than 1. So you can do this, and these are results that were even improved very recently. I did it in the 90s, and then Pierre-Louis Lyons in 96, and Vasseur 2010, and Vasseur and Yang 21, with this little Q here refers to Lorentz spaces, and there is a Q, it's larger than 4 tertals. So these are quantitative estimates. So now I'm going to refer to the notion of intermittency that was pushed by Gruich and then separately by Cheskidov and Schwittgoy. So Gruich, this assumed sparse upper level sets of high derivative. So again, what I mean here, it's a very quantitative statement, but what it imagine that you take one derivative, let's say, or 13 derivatives, you paint the region where originally the magnitude or one component is exceeding its average by much, and then you stick a rod in some direction and discover that that rod of a certain length sticks out 90% or 30%. So all these things become quantitative assumptions about the sparseness of the upper level sets. And you assume, based on experiments, that such a thing exists. Then you discover that the distance between these known results and the previous results that were known, the powers, you see, become close. So in the limit of high derivatives, the gap between known a priori estimates and conditions for global regularity vanishes as the number of derivatives tends to infinity. So again, in some sense, intermittency is controlled. So you cannot have singularities. Cheskidov and Schwittgoy defined intermittency dimensions in Fourier space. They're not the same thing, unfortunately, because these are all asymptotically equivalent, but not literally at finite Reynolds numbers. So, and these are kind of related to this highest wave number that we discussed. There is something called a Bernstein inequalities that tell you how large this Littlewood-Paley components can be. So you Fourier transform the velocity and you localize in wave number around 2 to the k. And then you can measure it in various integrals, very LP norms. And there is relation between them that are coming, they're rigorous, they're correct, but they come also from dimensional analysis. And then if they saturate differently than dimensional analysis, that implies some sort of intermittency in physical space. It's very implied because it's really on these components. And that intermittency, if that intermittency dimension is small, all of a sudden there is no intermittency, there is regularity. So this is a theorem. But as I said before, lots of assumptions before you get to the theorem. So in Navier-Stokes, the pressure is everything. The pressure is everything because if you knew something about the pressure, of course, everything is everything. If you knew something about the vorticity, it would be okay also. So regularity in Navier-Stokes refers to the absence of a divergence in the velocity. And this can be controlled from the pressure. And it is controlled from the pressure, for instance, in a multidimensional Burger's equation where there is compressibility, but there is no pressure. Then there is a maximum principle for the velocity, and there is no loss of regularity. So in the presence of viscosity. So the regularity theory in the Navier-Stokes theory, the pressure hinders a maximum principle, and therefore it is an essential ingredient for the regularity theory. And we saw in this morning's first talk how the importance of driving through pressure bounds. So driving through a pressure drop is it's the way to derive it. So the pressure in the Navier-Stokes equations in the absence of boundaries, so that means when the projection on divergence-free commutes with the Laplacian, so that is the case in periodic boundary conditions, is case in the whole space, and there are some other special cases in which you can do that. Then you can invert, you can commute the divergence equation through the equations, and then the pressure obeys this simple equation. So the pressure is defined up to a free, possibly time-depending harmonic function. And the equation doesn't see the viscosity. This is really just stating that divergence-free is preserved in time. So there is a certain formula that you can use in the whole space. And there is also a local representation. So by local representation, I'll explain in a second, you can decompose the pressure in two pieces, and all the information that you need for each piece is computed at a distance r that you choose from the place where you compute. So let me explain these two pieces. So this is a exact representation, and r is at your disposal. So the first piece is that I chose an average of averages. So this is an R average. So this is you take a ball of radius rho. You take the skin average, the average on the surface of distance rho from x, and then after you took that average, you average that in rho a little bit. And so this is one piece, and the other piece is, roughly speaking, there is another component that looks like this, is an average or displacements. So it looks a little bit or very much like a structure function, and these are Stokelets. They're very well-known objects. So this decomposition is straightforward. And all the information is at a ball of radius 2r here. So as I said, there is one more piece here. Pi is the anharmonic contribution. So the only contribution that this contribution sees doesn't see the harmonic piece. So the harmonic piece, in the harmonic piece, the pressure is of course equal to its average, so that piece is removed from pi. The p bar is bounded for fixed r, so you choose r to be at your choice, and then p bounded has some bounds that will imply regularity for Navier-Stokes. So if you can neglect pi, you are regular, and if you look at pi, pi is small if you have any kind of assumptions of continuity, for instance. So, and also this result about pi it can be used to show that velocity, if the velocity scales like, so if the structure functions are of order alpha, then the pressure is of order 2 alpha, something that in physics was well known but not proved. And this is a rigorous result from this very simple regular result. Was done in Fourier by Isett and Louis Sylvestre. I don't think he published it, but he knew it also. And this is in a paper from 2013. So basically, I think this is a very useful representation. In particular, relates assumptions about fluctuations near the wall to the pressure near the wall. So I think that these are important things that can be useful. So we were talking about conditional regularity for Navier-Stokes. We'll talk a little bit about the Euler equations, and then we're going to talk about relations. So the Euler equations are conservative equations. They don't have dissipation, and they're somehow behind the entire problems of understanding turbulence. So blow up is a famous problem, not less important than the Clay problem. maybe more important. So it's not known, just like the clay problem. So there are results, famous results of going back to J.T. Stewart and Childress, Yearly, Spiegel, Young, and then Gibbon, Focus, Doering, and Okitani. And they are stagnation type singularities. And a typical example is this slender vortices in which you have, you can think of it as 2.5 dimensional. There, the velocity depends on only 2 variables, and it has a certain profile in the vertical direction, and this is infinite energy because the z is unbounded. And then you can prove rigorously that this blows up, but the blow up in some sense comes to from infinity. There is a very nice result by Tariq El-Guindi that shows that axisymmetric solutions without squirrel blow up for small C alpha vorticity. So this is a case in which the solutions, the equation is well posed, but there is finite time blow up. However, it's not a case in which smooth solutions blow up, because in this particular case, if you start smooth, there is no blow up. So it's a somehow it's a result about rough data in some sense. So as we know, numerics suggest sometimes blow up, and vertex stretching is a basic mechanism, and alignment of vortex lines opposes blow up. So it is suggestive by many arguments that the underlying geometric structure for a blow up needs to be singular itself. So I drew here an X. That's my only picture of the day. So essentially, if you are assuming that your solution is blowing up in a self-similar fashion, and the structure itself over which it blows up is simple, then it's unlikely that that happens. So there are other examples in which you have 2 fluids with equal viscosities, and if, for instance, between a fluid and vacuum, we have two-phase situations where you can prove in some situations something called a splash, which is a technical term that refers to a singularity by osculation, by kissing smoothly 2 surfaces, or a splat, even a singularity that occurs on a line. Those are not likely to happen in in Euler homogeneous one single fluid or Euler. So here is the Bilkat-Omaida again. So if the time integral of the maximum vorticity is finite, there is no singularity in the Euler from initial data that are smooth. And if the direction field of vorticity is smooth in regions of high vorticity, then the Navier-Stokes solution is smooth, and the Euler equation require infinite velocity for blow up. So these are results that have been improved. And at this point, I'm making, let's say, making up a story. So at this point, this is not math. Vortex reconnection as a Navier-Stokes regularizing mechanism. So strong coherent vortices do form. They stretch. They become more intense, narrow vortex tubes. And these tubes approach at various angles, and it's numerically verified. And then they violate the assumption of smoothness of the direction field. So the gradient of psi becomes infinite, but there is an a priori bound for this gradient in large vorticities that is finite if viscosity is finite, and this is the initial energy. So then there is a reconnection, and which is a topological change. It's prohibited in smooth Euler solutions, but permitted in Navier-Stokes. It's permitted in the heat equation. And then there is a decay. So this part here of the talk is a story that I believe is true, but there is no proof. So I'm going to mention one more condition for regularity in terms of the pressure in the Euler equations. And because of that, I need this busy slide. So it's just annotations. This is the Lagrangian path. So it's called capital X, material derivative. And we have here the rate of strain matrix. And the rate of strain matrix has an equation, the S equation, where J is the antisymmetric part of the gradient. And it is really multiplication cross product by vorticity. So the equation here sees the Hessian of the pressure. So Hessian of the pressure is two derivatives of the pressure. So there are other equations here. This geometric depletion of nonlinearity had to do with the fact that the stretching equation of magnitude of vorticity is controlled by the direction field of the vorticity. So I'm not going to get into that. The S equation, please remember, refers to the evolution equation of the strain, rate of strain. And that equation is the source of the next result. So first of all, long ago, I proved that if the matrix, the Hessian is non-negative in a weak vorticity region carried by the flow, there is a blow-up. So here is a simplified version. This is an old paper. You take a marked point, assume that there is a time, and on that time, on the particular Lagrangian trajectory, the vorticity is bounded on that, all that trajectory and all that time. And then the Hessian of the pressure, again, along that trajectory is non-negative, meaning as a matrix, right? So for any vector, the scalar product of the pressure applied to the vector, dotted into the vector, is a non-negative number. So the pressure is a symmetric, obviously, it's a Hessian is symmetric, and it's a positive matrix. So you then assume that the strain, rate of strain at time 0 is large. And being large, it will have a direction in which is largely negative because it's trace free. Then blow up occurs if the time, this time of coherence times the size of the vorticity is large enough. So there's a quantitative quantity. It's really, it's based on the equation and some simple tricks. So it tells you that if you have a minimum of the pressure that's coherent, so the pressure Hessian points upwards, so it's not negative, and it's coherent long enough quantitatively in a region close to a region where the rate of strain is negative, is large, then you have blow up. On the other hand, this is a technical result, so I will comment the details in a second. So this is an exponential of a double integral of the Hessian of the pressure in one direction, one component, and the component is in these two vectors. So it's a matrix applied to the direction of vorticity, dotted into the direction of the time derivative of the vorticity, the SC. So if the negative part of this number is doubly integrable after an exponential, then there is no blow up. In particular, and this is maybe my comments in the next page will be better. In particular, if the maximum of this quantity is exploding in a 1/t² fashion, but the fraction, the coefficient there is less than 1, then you have singularity. No, you have no singularity. So that excludes singularity. So let me make a comment about this. First of all, obviously this one component is less than matrix norm. So in particular, if this quantity on the norm is finite, there is no blow up. And in particular, if the norm doesn't multiply by t minus t² is less than 1, there is no blow up. Now, what is this number 2? If you remember the condition, the vorticity or the gradient of velocity needs to blow up like 1/t in order to blow up at all, because if it blows up at a slower power, the Bill-Kato-Maida result implies regularity. So if one derivative blows like 1/t or less, then that's called type 1 blow up. And by dimensional analysis, I have here two derivatives, one more. If I have two derivatives, then the pressure would blow up like the power 2. So if you multiply this by t minus t squared, then you get a constant, less than a constant, that's called a type 1 blow up. And if the constant is less than 1, then there is no blow up. That's the meaning of this. The result can be, so here the remark was about the norms, but only one special component needs to be obey this kind of things. So again, this is important for the reason that, again, the pressure in some sense is the only impediment to understanding fluids. So also it is a little surprising because in the Euler equations, it's surprising to imagine that you can control everything only with the pressure. So there are models, famous local model by V.A. Voss, a less famous model in which you just replace material derivative by time derivative, and you get blow up, or the previous result in which you assume non-negative P and you get a blow up. So this is a remarkable contrast in my mind, that you can control everything only with the pressure. If you look at the S equation, that's what my comment is, that if you look at the S equation, if you give yourself the freedom to model P by something, like say the trace of S square or something like that, and then this blows up, no matter what you think about P, whereas in real life, P controls it. So this can be localized. I'm not going to bother you with this, but the only point is that you can measure all these things only in a ball around a point, and then there is no blow up in the region around that point, provided, in addition, that you didn't send that point to infinity in finite time. So this is this assumption in addition. All right, so let me talk a little bit about the implicit limit. So if you take higher Reynolds number limit, if you fix the time interval and you are in a regime in which you know the smooth Euler equation exists, then in the absence of boundaries, you got Euler equation with that initial data. So in a non-smooth regime or with boundaries, there are major open problems that are really the crux of the matter. So if you force the equations, for instance, the correct forcing, which is having boundary conditions, and take time to infinity, you get a long time behavior, and then a Reynolds number to infinity, then you will end up with some statistical solutions. And statistical solutions, before you take the limits, the Reynolds number, practically you would like to take an observable of the solution of the Navier-Stokes equation, let's say a component of velocity or an increment or a derivative you can, and take time averages. And then after you took time averages, you take the limit of Reynolds number to infinity. If this quantity is a numerical number, then you get actually a numerical answer, and you get a measure. So this is, again, in my mind, this is the most important object in turbulence, but we do not have a unified way of defining it. So I'm going to skip over this in terms, I think I am probably closer to the end. So it is known that if you are in periodic space,
and so, Peter, it's 50 minutes. So
how much?
You are exactly 2 minutes before 50, so like 48 minutes already.
Okay, all right. So I'm going to skip on the finite time, no boundaries is understood. Rough data, we understood recently with Theo Divas and El-Gindi, a strong result on arbitrary time and strong convergence with data that are a little rougher. So the gradient of velocity is only bounded, but discontinuous, perhaps. I want to make a comment about so there is rate of convergence. I will skip even this. So with boundaries, we don't know much. So rather than talk about it, there are some assumptions. Their results without assumptions are few, and they are only on very short time, real analytic data, or the vorticity supported away from the boundary, or analyticity only near the boundary. This is a result of Kukavica, Vikol, and Wang from 19 and improved recently with Nguyen. And the restrictive symmetries by the authors here, Helena and Milton, and Anna Matsukato, and Taylor and Kelleher. So those are all the results that are unconditional. Conditional results abound, but the observation of Kato was that you have to have vanishing energy dissipation. And this vanishing energy dissipation condition holds if you have strong convergence, no matter what. So there are some results in which you don't have strong convergence under the assumptions, let's say, of some scaling internally, and then you can go to Wick's limits to Euler equations inside. But then under the assumption of some scaling inside, you go to the Euler equations. So that would be perhaps satisfactory from the point of view of assuming turbulent behavior. But the Euler equations you can go to are very strange. So I'm not going to talk about that. I want to finish with multi-scale solutions. So remember that in the beginning I said there is this assumption that nu times gradient u square being finite implies somehow that we need singularity, but it's really only an asymptotic statement. So there exist solutions in any open set in R3 for any number between alpha and between 1 and 3. There exist families, by which I mean with viscosity going to 0, of smooth, stationary, that means time-independent solutions of the forced Navier-Stokes equations that are smooth and compactly supported velocities. The gradient of the pressure is compactly supported and smooth, such that this product, which is allegedly the energy dissipation, is a positive constant independent of nu as nu goes to 0. There is an inertial range such that dissipation wave number diverges with nu goes 0. And moreover, the energy spectrum has a power law, modulo constant, and the power law is this alpha that I start with. And as you very astutely observe, 5/3 is in the range. And this is singled out by being the only one in which the prefactor is scale independent. In other words, doesn't depend on the omega. The force F is smooth, compactly supported, and bounded in LP. And the little details here is that P is not just anything, but depends on alpha. So for instance, is 18/11 in the case of the Kolmogorov alpha, okay? So I'm not going to talk about the construction, but the construction is done by taking Euler solutions that are smooth, compactly supported, with swirl, axisymmetric. So these are constructed after Gavrilov by Vikol and Jun-Ho La, myself. And you turn them around, squeeze them, put them, make a gear. You can link them if you wish. And because they don't talk to each other, you can add them. So that's the construction. I'm not going to get into the details of the construction. It's this thing is described. So the main point here is that these are rigorous statistical solutions of Navier-Stokes with force and infinite time, and a sequence of them that have all this. This is not turbulent. It's frozen in time. It's complicated, and near them there could be interesting dynamics, but they are smooth, steady solutions that exhibit all these complications. They're rigorous, everything is correct, and they are essentially a caveat. It's a warning. So let me finish with my conclusions. I think universality and turbulence is a tall order. So definitely in 2 dimensions is a very tall order, and in 3D, I don't know. Many in the physics community, people don't pay attention very much to the nature of the forcing, and part of my caveat or warning is the nature of the forcing. So if you take long time, high Reynolds number regime, you end up with some form of statistical solution, hopefully. And if you have boundaries, the limit is open. The zeroth law, anomalous dissipation of energy, in the absence of singular forces for a long time average, rate of dissipation of energy is open. The spectral information, beware of models. They're examples. So they're examples of Kolmogorov laws, but there is excessive vertical across wave number energy transfer. That means there's a forward energy transfer, for instance. Very interesting results. But what's underrepresented is the lateral local spreading in wave numbers energy transfer. So I don't want to get into the details of this, but if you linearize Euler or Navier-Stokes equation around Kolmogorov states, you see immediately how energy wants to move laterally and spread laterally. So this is what I'm saying. So the moment in which that in turbulence sometimes is locality and wave number. So that allows for this process of transferring the spreading of energy that we don't understand. So I would like to end here with the warning about forcing. Recently, there have been results about non-uniqueness with singular forcing. There are results about behavior under a number of very, let's say, rough forces that are perhaps not what we should look at. So I think that when we pay attention to experiments, we should pay attention to the nature of the situation that we are actually have some confidence about universality. And maybe we should try to model that. So I'm stopping here.
Thank you very much, Peter. Already Uriel has his hand on, so